Hi guys! In this video we will talk about LDF, or known as London Dispersion Forces. These forces is one of intermolecular forces, and it's the weakest of all IMF. London Dispersion Forces exist in all atom and molecule, but of importance for neutral atom and non-polar molecule. Did you know that London Dispersion Forces was named after physicist Fritz London? In 1930, Fritz London proposed the existence of London Dispersion Forces. He said that neutral atom or nonpolar molecule does not have dipole-dipole attraction because these particles does not have permanent dipole. But these substances also become liquefied, and that's mean there must exist some kind of temporary attractive interaction between particles. Formation of LDF. First of all, let's imagine we have an atom with a nucleus with a positive charge, and there are 6 electrons around the atom. Imagine this atom is nonpolar. Then, the electrons are evenly distributed in the atom. Now, as these electrons are constantly moving around the nucleus, there's going to be a moment where more electron polarized on side as opposed to the other side. So, due to the random motion of the electrons about the nucleus, at some point most of the electrons might be on the left side and some will be on the right side. This means that we can have uneven distribution electrons. So this atom is temporarily polarized where the side that is an electron deficient has a partial positive charge, while the one that have more electrons has a partial negative charge. Now, this atom has become a momentary dipole. So why it's a momentary dipole? It is because it is not a permanent phase and doesn't last long because it happens for a very short time. Next, this momentary dipole can easily cause another neutral atom, nonpolar, to turn into a dipole so it can induce another dipole neighboring atom in a similar molecule. For example, we put one neutral atom next to momentary dipole in gas phase, then the electrons in the neutron atom will feel a force of attraction, thus make the electrons cloud will become distorted and accumulate at one side or repel away to other side according to the partial charge in the momentary dipole next to it. To conclude, the side that have partial positive will feel a force of attraction towards partial negative charge in the momentary dipole next to it. That force of attraction that connects those two atoms is called London dispersion force. Now, let's focus on polarizability. Polarizability is the ease with which the electron cloud can be shifted. The easier the electrons can shift to one side, the easier a temporary dipole forms, and that means stronger London dispersion forces. Now compare fluorine, F2, and iodine, I2. 2 is small, while I2 is much larger. In iodine, the outer electrons are further from the nucleus and are held less tightly, so the electron cloud can be shifted more easily. That means iodine has higher polarizability. Also, F2 has 18 electrons, while I2 has 106 electrons. More electrons mean more movement and a higher chance of forming a temporary dipole. So, as we go down group 17, size increases, electrons increase, polarizability increases, and London dispersion forces become stronger. So, does every molecule have the same LDF strength? Not quite. There are 2 main things to look for. First, size and molecular weight. The first major factor is the size of the atom or molecule, which determines its polarizability. In smaller atoms, like helium or neon, the electrons are held very tightly by the nucleus because they are in shells close to the center. This makes the electron cloud stiff and difficult to distort. However, as we move down a group in the periodic table, for example from fluorine to iodine, the number of electrons increases and they occupy higher energy levels further from the nucleus. Because these outer electrons are shielded by inner shells, the nucleus has a weaker hold on them. This results in a large diffuse electron cloud that is easily distorted. We say these larger atoms have high polarizability, meaning a temporary dipole can be induced much more easily. The more easily the cloud can shift, the stronger the resulting London dispersion forces. The second factor is shape. Think of it like Velcro. If you have 2 long straight strips of Velcro, they stick together really well because they have a lot of surface area in contact. But if you ball that Velcro up into a sphere, they barely touch. It's the same for molecules. N-pentane is a long, straight chain, so it has more surface area for LDF to grab onto, giving it a higher boiling point. Neopentane is branched and bulky, so its LDF is much weaker. Let's see the real-life application of LDF. Ever wonder how graphite are easily to break than diamond even though both of it are made of carbon? The way of those atoms connect change everything. For diamond, each carbon atom bonded to 4 carbon atom. It will form a 3-dimensional giant covalent structure. This covalent structure is extremely strong and hard to break. For graphite, carbon atoms are arranged in layers of interconnected hexagonal rings. The covalent bonds are incredibly strong within the carbon sheet, but the forces between the sheets are just London dispersion forces. Because of LDF are weak, the sheets cannot hold onto each other tightly. Therefore, they easily slide past one another. So, to wrap everything up, London dispersion forces might be the weakest of the intermolecular forces, but they are everywhere. Every single molecule has them, whether they are polar or not. As we've seen, it really comes down to two main things: how big the molecule is and what shape it's in. We saw that as atoms get larger, their electron clouds get much easier to shift. Fluorine stays a gas, but iodine has enough stickiness to be a solid at room temperature. We also looked at how shape matters. Like our pentane examples, the one with the most surface area wins. LDF is basically the hidden glue of the molecular world. It's what decides if the substances around us are solids, liquids, or gases. Thanks for listening.